Hello everyone and welcome to this Channel Talent headliner on the real-world applications of vectors. My name is Dr. Robert Whittaker and I'm a lecturer at the University of East Anglia in Norwich. And this is a picture of our beautiful campus on the edge of the city. Do have a look at our website if you'd like to find out more. So what are we going to cover? Well, in this pre-recorded video, I'll be talking about what vectors are, how we can represent them mathematically. I'll tell you a little bit about some of the mathematical operations that we can do with vectors before going on to talk about something known as abstract vectors in mathematics. And I'll finish up with some examples of some real-world applications of vectors. Then later on in the live online session, I have a quick recap of some of the things that I've covered in this video before going on to look in detail at some of the real-world applications of vectors. Okay, so let's get started. So what is a vector? Physically speaking, a vector is a quantity that has both magnitude and direction. And this is distinct from a scalar quantity, which you just have a magnitude for. It's easiest to think of this in terms of some examples. So scalar quantities include things like density, pressure, and temperature. So for each point in space and time that we might be interested in, the temperature is just a single number. So it might be 5 degrees or 10 degrees or 20 degrees, but there's just a single number for that. Whereas vector quantities, for instance, velocity, there's a magnitude and a direction. So in terms of velocity, we don't just want to know how fast something is moving, we want to know which direction it's moving in as well. So there's the magnitude or speed that tells you how fast you're going, but there's also the direction that tells you which way you're going. And it's similar for the other quantities as well. So for force, we don't just want to know how big the force is, we also want to know which direction the force is applied in. And obviously that makes a big difference. If I'm applying a force upwards on something, I might be able to keep it up in the air like this. If I'm applying a force sideways, then it's not going to be kept up in the air at all, and it will shoot off to the side instead. So the direction that we get from vectors can be very important. There's also a more abstract concept of what a vector is in mathematics, and we'll come on to that a little bit later. So for now, just think of vectors as being physical things with magnitude and direction. So how do we represent vectors mathematically? Well, if you see them written down in print, they're normally written in a bold font, and when you're handwriting them, at least at university, we typically underline our vectors. At school, you might see people writing little arrows across the top. That's fine as well. I'm going to use the convention of underlining them here because that's what we do at university. In terms of actually sort of representing them numerically, we'll often use the coordinates or components of a vector, often with respect to Cartesian axes. So what we do is we take our physical vector and we say, well, how far along has it gone in the x direction? That's one component. How far in the y direction? How far in the z direction? And that gives us 3 components, and we then write them either in a column or a row to form a vector. More generally, you can think of a vector as being a sum of different multiples of a number of fixed vectors known as basis vectors. So if I define 3 fixed vectors, one in the x direction, one in the y direction, one in the z direction, you might see them written as vectors I, j, and k. I've used E1, E2, and E3 here to be a little bit more general. And then we can think of our vector V as being V1 times E1 plus V2 times E2 plus V3 times E3, where the V1, the V2, and the V3 are the components of the vector with respect to these 3 basis vectors. And you'll notice in both these cases, I had 3 different components, and for a given vector, the number of components will always be the same, and it's known as the dimension of the vector. So if we're dealing with things in 3D space, we'll have 3 components. We might want to deal with things in 2D space and have 2 components. If we've got some more abstract vectors, we might have more components than that. So we might have 4 components, 5 components, even hundreds or thousands of different components for more abstract vectors. So what operations can we do with vectors? So we've got these sort of mathematical objects, we want to be able to combine them in some way and produce new vectors and scalars as a result. So suppose we've got 2 scalars a and b and 2 vectors u and v here with components u1, u2, u3 and v1, v2, v3. How can we combine these objects to produce new vectors or scalars? So one thing we can do is vector addition. So this is sort of somehow adding up 2 vectors to create a third vector. And geometrically, you could sort of draw the vector as being a line from one point to another with the right length and the right direction. And if we want to add up two vectors, we draw the second vector starting at the end of the first vector, and then the result of the sum is the vector that goes from the beginning of the first vector to the end of the second vector. Physically adding up vectors is somehow combining the two vectors together. If we're applying two different forces on an object, for instance, then the total net force that we're applying is the vector sum of the two individual forces. And in terms of components, we just add up the first components, add up the second components, and add up the third components to get the three components of the new vector. We can also do scalar multiplication of vectors. So this is where we take one vector and we just multiply it by some scalar quantity. So that's just multiplying it by a number. And geometrically, that just has the effect of keeping the vector in the same direction, but scaling the length of it by the number. So if we do 2 times u, we're going to get a vector with the same direction as u, but twice as long. We can also multiply by negative numbers, and that just flips the direction to point 180 degrees out. We can also calculate the modulus or magnitude of a vector. If we know what the components are in Cartesian coordinates, a little bit of Pythagoras' theorem will tell us that if we square the components, add them up and take the square root, that will give us the physical length of the vector. And we can use this idea more generally to calculate the modulus or magnitude of other vectors too. If you've done anything about vectors at school, you might have come across something known as the scalar product or dot product of two vectors. This is some sort of mathematical operation that combines two vectors and comes out with a scalar quantity in the end. We can work out what this is in terms of the components of the vector. And what's nice about the scalar product is it gives us a way to calculate the angle between two vectors. So if we've got two vectors u and v, if we do u dot v and then divide by the modulus of u and the modulus of v, we'll get the cosine of the angle between us. So this allows us to calculate sort of how similar the direction is of two vectors. And finally, being a bit more general, we can also have functions of vectors. So you've met functions of normal numbers. We can also have functions of vectors. So we have an input, and then we apply our function to it, and we get an output. And in this case, we want the input to be a vector and the output to be another vector. And these functions can describe various transformations, such as rotations or reflections, or more general deformations of space that will somehow alter the vectors that we've got. And a particularly important class of functions are known as linear functions. And a vector function f is said to be linear if it satisfies the equation in the yellow box there. So for all scalars a and b and for all vectors u and v, the function is linear if f applied to au plus bv is the same as a times f applied to u plus b times f applied to v. And if that holds for all possible scalars and vectors, then the function is said to be linear. And one thing to note is, even though the definition only has 2 bits being added together inside the function, if it works for 2, it will also work for any other number as well. So for example, if we had f of au plus bv plus cw, if f is linear, then that will be the same as a times f of u plus b times f of v plus c times f of w. Okay, so why are these linear functions useful? Well, it turns out that if we know how a linear function transforms the 3 basis vectors that we've got, then we know everything we need to know about the function. So if we're trying to take this function and apply it to a general vector v, if we write v in terms of its components and the basis vectors as v1e1 plus v2e2 plus v3e3, and then apply the function f to it, because f is linear, we can write that as v1 times f of e1 plus v2 times f of e2 plus v3 times f of e3. And then if we know how f acts on these 3 basis vectors, we know what those f of e1, e2, and e3 are. They're just going to be some other vector. So let's suppose that f of e1 is equal to capital F11, capital F21, capital F31 as the components of the vector. And similarly for the function applied to the other 2 basis vectors. So these 3 vectors, and we've chosen to write down their components as capital F with different subscripts on. So there are 9 different components there that we're interested in, And if we're applying f to some general function v with components v1, v2, and v3, this is what we're going to get. And we can now use the rules for scalar multiplication and vector addition to combine all those into one single vector. So we have the first component is f11 v1 plus f12 v2 plus f13 v3, and we get similar expressions for the other two components as well. And then this particular way of sort of adding up these 9 components that have come from the function and the 3 components from the vector is really common in mathematics, so we develop a special notation for it. We write the 9 components from the function as a 3 by 3 array, and we write the vector as a column vector. And the 3 by 3 array we call a matrix, and then we have a rule for multiplying a matrix by a vector, which gives us exactly the components that we've got on the second to last line. So if and when you come across matrices, one way of thinking about matrices is that they represent linear functions of vectors. And these are really important for being able to work with vectors and being able to transform vectors, particularly in some of the applications that we'll look at. Okay, so now we'll think about the more abstract idea of vectors. So we've seen physical vectors and we've seen how we can use those. But in mathematics, it's really useful to work from a precise set of rules or axioms that govern how a particular set of objects behave. So what do we actually need to work with the vectors that we've just seen? So we need a set of vectors to work with, some sort of collection of objects. We need a way to be able to add 2 vectors together. We need a set of scalar quantities, and we need a way to multiply the scalars by the vectors to get another vector. And optionally, we may have a way to calculate the size or magnitude of a vector, and we may have a way to compute a scalar product of 2 vectors. But it turns out these 2 bits at the end are slightly less important, and it's the first ones that are actually more crucial in getting some set of objects or vectors that we're able to do mathematics with. So in mathematics, mathematicians have thought about this, and they've come up with this concept of something called a vector space. And this is a sort of fundamental thing that captures all the important properties that we want vectors to have. A vector space is a set of objects that comprises a set of scalars, which we'll call f, and a set of vectors that we'll call v, and the operations for combining them in the right ways. And there are a number of rules that have to be satisfied for this collection to be a vector space. So first of all, we need multiplication and addition to work in the set of scalars f in the usual way. And it turns out f needs to be a mathematical object known as a field. We also need vector addition to work in the usual way. And it turns out that v needs to be a mathematical object known as an abelian group. We also need to be able to have scalar multiplication of the vectors. So if we take a vector from v and a scalar from f and multiply them together, we need a way of coming out with a new vector in v. And then we need the scalar multiplication and the vector addition to be somehow compatible with each other. So sort of usual rules of algebra and arithmetic need to work out in a certain way. And there's a number of set rules to do with sort of expanding brackets and making sure that 1 times the vector is the same vector. And putting all these rules together, they're known as the axioms of a vector space. And what's really sort of useful about these is if we've got a set of objects that obey these axioms and we can prove something just using the axioms, we'll know that that will be true for all possible sets of objects that satisfy these same set of axioms. And that's really useful mathematically to be able to do that. So what sort of things can we form vector spaces from? Well, the set of scalars f is usually the real numbers, but it could be the complex numbers, and there are other more exotic options that we can choose too. The set of vectors v can be any set that satisfies the axioms, so this includes physical vectors. We could also use functions and think of them as vectors, and again there's more exotic mathematical objects you can come up with that still satisfy these same set of axioms. The vectors that we write down can still usually be described by a set of numbers or components, and each of these components is the size of some sort of abstract component in the vector. And as I've already said, if we've got something that satisfies the axioms, we can use that to prove things about how vectors behave. And anything that we prove will be true for every vector space, not just those involving the physical vectors. And these abstract vector spaces are really important, both in mathematics and in terms of various real-world applications, and we'll see some of those in a bit. Okay, so just to finish up, I'll give you some ideas of some of the real-world applications of vectors that we have, and we'll discuss some of these in more detail in the live follow-up session. So for physical vectors, we can use them to help model the movement of bodies that are subject to forces. So this might be projectiles, sort of chucking a cricket ball, or it might be the orbits of planets. Both of these have bodies that are affected by forces, gravity in this case, in different ways. We can also use mathematics to model and understand how fluids move around, and also aerodynamics for things like racing cars. We can use vectors to describe the deformation and vibration of elastic solids. That might be important if we're modeling earthquakes and how different buildings will behave when they're hit by an earthquake. Perhaps more unexpectedly, we can also use physical vectors to help us compress video files. So to make sure our video files aren't larger than they need to be, there's various techniques that we can use involving physical vectors and rotations and transformations of 3D space. And then moving on to abstract vectors, so these are still vectors in a mathematical sense. They also have a number of uses in the real world. We can use them to help solve differential equations. We can use them in signal processing. So if you've got some receiver receiving radio waves and you want to sort of interpret what the signal is that you're getting, vectors can come in handy there. We can also use them in image compression techniques to help keep computer file sizes down as small as possible. Google's PageRank algorithm for web searches relies on some ideas from vectors as well. And generative AI also makes extensive use of vectors. And we'll discuss some of these applications in the follow-up session that's live online. So I hope very much I'll see some of you there. So thank you for your time, and hopefully I will see you in the live session.